Hello, everyone. Thank you for attending my talk, and thank you especially to the organizers. I'd like to tell you today about a new invariant developed by Ito and Takimura called the splice-unknotting number of a knot. This invariant in general provides an upper bound for the crosscap number, and in the alternating case for prime knots, the crosscap number and the splice-unknotting number are equal. Outline for the talk is, first I'll define the invariant. Then I'll give some background reviewing crosscap number, related invariants, talk about construction of state surfaces, especially talk about how they pertain to alternating knots. Then we'll talk about the main result, briefly talk about the proof. Then I'll mention some corollaries, computational results for myself, and then corollaries from Ito and Takimura relating to Jones polynomial and hyperbolic volume. And then finally, at the end, I'll mention another new invariant developed also by Ito and Takimura that is similar in construction and turns out to be equal to what I'm going to call the overall genus of a knot, which I'll discuss in section 2. Okay, let's get to it. First, splice is like what is often called a smoothing. I'll be talking about smoothings later as well. So for a splice, you're getting rid of a crossing. Kind of in the usual way. There are 3 types. One type is the type that respects the orientation. So we're only dealing with knot diagrams here. And notice that if you have a knot diagram and you split it open in the way that respects the orientation, you always get a diagram of a 2-component link. All of these pictures, by the way, are, you can also have the mirror image. So anything that respects orientation, I'm going to call a Seifert splice. If you have something that doesn't respect orientation, it either is a Reidemeister 1 move that gets rid of a crossing, or I'll call it a U- splice. So a U- splice is a splice that does not respect orientation and is not a Reidemeister 1 move. And notice in particular that this always gives you a knot diagram with 1 less crossing than the one you had before, as does a Reidemeister 1 splice. So notice that given any knot diagram, you can perform these moves. If you have n crossings, you can perform a sequence of n of these moves, depending on what order you do them on the crossings. And any of those sequences ends with a diagram of the unknot. Well, look at all of those sequences given a diagram and choose the one with the smallest number of these U- splices. And that is what we'll call U- of D. And take that quantity, minimize it over all diagrams of the knot, and that is the splice-unknotting number of a knot. A couple quick examples of this. First one is for the trefoil, the splice-unknotting number is equal to 1. And the reason why it's equal to 1, well, this sequence right here is a splice-unknotting sequence of length 1. And by length, I mean the number of U- splices. So we splice this crossing, then we get this diagram here, perform 2 Reidemeister 1 moves, we get the trivial diagram. So the splice-unknotting number is at most 1. It's also at least 1 because the only knot that can have splice-unknotting number equal to 0 is the unknot. Another quick example. This won't tell us what the splice-unknotting number of the figure 8 knot equals, but it will tell us that it's at most 2 because this is a splice-unknotting sequence for the figure 8 knot of length 2. Later, we'll come back to this example to get the reverse inequality. Okay, that's the invariant. Next, crosscap number of a knot measures the complexity of the simplest possible one-sided spanning surface for the knot. Meaning, we're looking at non-orientable surfaces whose boundary is equal to the knot. And you choose the one that's the simplest in the sense that it has the fewest holes. And the number of holes in it is called the first Betti number. That's also equal to the rank of the first homology group. It's 1 minus the Euler characteristic. And it's the number of cuts required along properly embedded arcs in the surface to reduce your surface to a disk. So, for example, a Mobius band has first Betti number 1 because if you cut it once along an arc, you get a disk. And you can verify that that's consistent with the other descriptions. The classical genus of a knot is take the simplest 2-sided surface spanning the knot and look at its genus, by which we mean take that surface with boundary equal to the knot, abstractly cap it off with a disk. Now you have a closed orientable surface, and the genus of the knot is the genus of that capped off surface. And that genus is also equal to half of the first Betti number of this simplest two-sided spanning surface. The overall genus, which is sometimes denoted with a gamma, I've denoted it beta 1 of k, which of course is an abusive notation because strictly speaking that is 1. So this overall genus of the knot is you take the simplest surface, don't care about it whether it's one-sided or two-sided, and look at its first Betti number. Okay, so these three invariants measure the simplest spanning surface for a knot, depending on whether you want the surface to be one-sided, two-sided, or whether you don't care. And notice that this overall genus is always the smaller of the crosscap number or 2 times the genus. And the reason why the 2 is there is because of the 1/2. Okay, next thing I want to review is state surfaces. For state surfaces, first thing you want to do is you want to smooth every crossing in the diagram. And smoothing is like a splice, except after you get rid of the crossing, you want to keep track of the fact that there was a crossing there by drawing in an arc, and you want to keep track of the over-under information by labeling the arc with an A or a B. After you take your diagram and you smooth every crossing, you get what's called a state, which is a collection of circles connected by labeled arcs. From this state, we'll build the surface in 2 steps. First step is we take each circle and cap it off with a disk. In this picture, you want to think that there's these 2 small yellow disks, a larger yellow disk here, and then a small orange disk in front or on top of the yellow disk. Then we finish building the spanning surface by attaching a half twist band at each crossing, following the type of crossing. And so this is the result of this construction by attaching the bands there. Seifert's algorithm is a special case of a surface obtained from Seifert's algorithm is a special case of a state surface. Namely, if you take the state in which all of your smoothings respect orientation, the construction in that case is called Seifert's algorithm. And it's a classical theorem proven first in the late 50s by Murasugi and Crowell using the Alexander polynomial, and later geometrically by Gabay, that Seifert's algorithm on an alternating diagram of a knot always produces a surface that realizes the classical genus of the knot. And more recently, Colin Adams and I proved that a similar result holds for the crosscap number and the overall genus. Namely, given any alternating diagram, you can look at the state surfaces from that diagram, and one of them realizes the crosscap number, and one of them realizes, at least one of them realizes the crosscap number, at least one realizes the overall genus. And of course, to realize the crosscap number, you insist that that surface not only have the right first Betti number, but that it be one-sided. Okay, and we'll use that result later. Now on to the main result. The first part, due to Ito and Takimura, is that the splice-unknotting number is always an upper bound for the crosscap number of any knot. And the idea of the proof is to take a splice-unknotting sequence of minimal length, meaning the smallest possible number of U- splices from the best possible diagram. And I'll do this with an example in a moment. Take that minimal length sequence and then put it in reverse. And when you put it in reverse, we'll use it to build a one-sided surface spanning the knot. And the key is that that spanning surface is going to have a first Betti number equal to the splice-unknotting number of the knot. And then it follows that the crosscap number of the knot is at worst the first Betti number of that surface, because the surface is one-sided, and that first Betti number equals the splice-unknotting number, giving the result that we want. Okay, so how does this put it in reverse construction work? Well, let's go back to the example from earlier with the figure 8 knot. We have the splice-unknotting sequence of length 2, meaning we have these 2 splice-unknotting moves. Now, when we put it in reverse, what we're going to do is we're going to build up a surface, starting with a disk spanning the unknot. And what we have to do is put these moves in reverse. And so I need to tell you what happens when we put an R1 move in reverse? What happens if we put a U minus move in reverse? Well, for an R1 move, we just do an isotopy. So in this case, after reversing the two R1 moves, we still have a disk. And then for our U minus splices, when we put those in reverse, what we're going to do is we're going to attach a crossing band, just like in the state surface algorithm. And so in this case, we attach a band here, and we attach a band there. So we've attached two bands corresponding to the two U minus splices, and as a result, we get a surface whose first Betti number is 2. And the reason why that is because if you cut along each of these bands that you attached, you get back to the disk, and the first Betti number is the number of cuts required to take your surface and turn it into a disk. Finally, why is this surface one-sided? Well, first of all, there has to be at least one U minus splice in the sequence because your knot is non-trivial by assumption. And the only knot with splice-unknotting number 0 is the unknot. Therefore, we attach at least one of these crossing bands. Now, think about what happens when you attach the first crossing band. Well, you get something with Betti number 1, but its boundary is a knot. And the only possibility is it must be a Mobius band. And then we attach more stuff to it, but that Mobius band is still a subsurface, and therefore what we end up with has a Mobius band contained within it, therefore it's one-sided. And so what we end up with, as needed, is a one-sided surface whose first Betti number equals the splice-unknotting number, giving us this inequality. Okay. In the alternating case, we get equality. And to prove that equality, we need the reverse inequality from before. And here's the basic idea. The basic idea is because we have an alternating knot, we can find a surface that realizes the crosscap number. We can find that surface and realize it as a state surface. Well, if it's a state surface and it's one-sided, there's got to be some crossing band where the orientation on the knot is not coherent with an orientation locally on the surface. In other words, there has to be a crossing band that looks like this or this. And therefore, we can cut the surface open along one of those crossing bands. And then, hopefully, and I'll talk about the hopefully in a minute, hopefully we can keep doing this all the way down until our surface is a disk. If we can do that, then, well, we assumed at the beginning that our surface had first Betti number equal to the crosscap number. And that first Betti number is the number of cuts required to take it down to a disk. And that number of cuts, well, each cut corresponds to U minus splice. So we get some sequence of U minus splices, and the number of U minus splices in that sequence is an upper bound for the splice-unknotting number. In principle, there could be a shorter splice-unknotting sequence, but we have an upper bound. And therefore, we will have proven the reverse inequality and the theorem. Okay, well, I explained a minute ago why you can perform at least one of these cuts that corresponds to a U minus type splice, but why can you keep doing it? Well, there is a concern, and the main issue that comes in is illustrated by the following example. So the 910 knot, here's a diagram of it, and this knot has only one state surface of minimal genus, and it's the one that I've drawn here. It's got this bridge coming over the top, and the first Betti number is 3. I could reduce this to a disk by cutting here, here, and here. But of those cuts, only one of them is the allowed type in terms of the orientation on the knot, and that is to cut at one of these orange crossings right here. But when I cut at one of those orange crossings and perform a couple Reidemeister 1 moves, we get this. And this is a possible problem. And the problem is that this knot is composite. Now, why is that a problem? It's a problem because the theorem assumes that our knot is prime. Okay. And why do we assume that it's prime? Well, the issue is that this is false. For example, if you connect some of the 7-4 knot with itself. And the issue is that the crosscap number of the 7-4 knot is greater than the overall genus of the 7,4 knot. So the concern is, well, sometimes you have to deal with these prime knots, and the theorem overall is false for the prime knots, or sometimes you get these composite knots. The theorem is false for composite knots. But fortunately, in this case, the crosscap number of each component that we get is equal to the overall genus, and it turns out that even when you're stuck getting a composite knot after your splice, you can always ensure that every prime factor has this property, and it turns out that that property is enough to make the theorem true. In other words, a more general version of the theorem is true, in which the knot either is prime or it's composite and every factor has overall genus equal to the crosscap number. Okay, so that's the main result. Briefly, I want to talk about some corollaries. First corollary, the one that I pursued, is computational. Computing the crosscap number of an alternating knot is not that easy to ask a computer to do for a few reasons. One is there are a lot of states from a diagram, and even if you can narrow the list of possible states to look at down, it's not that easy to encode them. Fortunately, this splice-unknotting number is easier to compute. I did this using Gauss codes, and using Gauss codes, I computed the crosscap numbers of all prime alternating knots up through 13 crossings. Some of these values were new for 11 and 12 crossing numbers, and number knots as well. Ito and Takimura obtain corollaries to relating to the Jones polynomial and hyperbolic volume. Using a result from Kalfagiani and Lee, they show that the splice-unknotting number, which is equal to the crosscap number, is a lower bound, or is bounded above by two quantities. One of them is the sum of the penultimate coefficients, or that sum plus 1, and the other is the spread or span of the Jones polynomial. The second corollary, using a result of Fuder, Kalfagiani, and Purcell, shows that the splice-unknotting number provides upper and lower bounds for the volume of a hyperbolic alternating knot. Okay, finally, I want to mention a related invariant because the construction is so similar. So here's the construction. This is the move. And you can use this move together with Reidemeister 1 moves to turn any knot diagram or link diagram into a diagram of the unknot. And the reason is, given a crossing, you can split it open by performing that move and then performing a Reidemeister 1 move. Okay, so then you look at your diagram, you look at all possible sequences of this B sub L move together with R1 moves, taking your given diagram to the unknot, and of all those sequences, choose the one with the smallest number of these B sub L moves, and then minimize that over all diagrams of the knot. That's this new invariant. And Ito and Takimura prove that this invariant always provides a lower bound for the overall genus of a knot, and that it equals the overall genus when K is alternating, whether your knot is prime or not. Let me put up my references, and thank you again for your attention, and thank you very, very much to the organizers.